Hey, let's do some alkene reactions. We are in Key Concepts, Unit 2, Part 4, and we already did this first reaction, but let's just highlight it one more time. It's a nice quick mechanism that actually it's going to be similar to some other reaction mechanisms we'll see in this video. Okay, so Key Concepts, Unit 2, Part 4 begins with the halogenation of alkenes. And that's where, well, what does this mean, halogenation of alkenes? We'll get an alkene. I'll put it down here at the bottom. Let's slide up a little. Suppose we have a ring so we can see the anti-addition. Let's see, how about this one? How about we take cyclopentene and we'll put a methyl group right here. And if you want to just draw it skeletal drawing like that, you're done. But you know what? I'm going to put a CH3 group, right? My guideline is whoever's drawing it gets to decide how to draw it. I'll throw in CH3 in there. Let's halogenate this. And we have the choice of two halides, either chlorine or bromine. Both work. I'll use bromine today. Okay. And then we're going to do the full reaction mechanism as a review. So step one, let's show some covalent bonds. So the Br2 molecule has one single bond. And in the first step of the mechanism, the pi electrons of the double bond are going to connect to one of the bromines. Oh, you know what? I don't know if in the past video we talked about why these electrons, which are negative, yeah. Why are they seeking this non-polar molecule, right? There's no positive charges there. Well, what intermolecular force makes Br2 a liquid at room temperature? That's kind of interesting. Br2 is a liquid at room temperature. So those Br2 molecules are sticking together to form a liquid, even though there's a lot of thermal energy bouncing around. Somehow they stick. They stay as a liquid. Well, bromine attached to another bromine are the identical elements, so there's no difference in electronegativity. This is a completely non-polar covalent bond, which makes the entire molecule non-polar. And non-polar molecules stick to other non-polar molecules by van der Waals forces or London dispersion forces. And how do those work? Well, we talk about a temporary dipole or some type of imbalance. And the way I imagine it is I should have popped up the periodic table. I believe bromine's element 35. I'm not positive. It's got a lot of electrons. And in a bromine atom, you would see all those electrons filling shells. The outer shell would have 7 electrons, yada, yada, the whole thing. Most of the time, those electrons are symmetrically distributed, right? Why would one side of the atom have more than the other side in terms of numbers of electrons? But electrons are in motion, especially if we think of them as particles. So it's possible, as these electrons are flying around the bromine atom, you might get an extra one on one side compared to the other side. And that's no different for the entire molecule, right? So there's 2 electrons being shared here, but there's all the core electrons, right? There's the 1s electrons, the 2s, the 2p. Yeah, there's a bunch of inner electrons that are just kind of flying around the nucleus. And what happens if, the lone pairs up here on the bromine just kind of sneak over a little bit onto the other side? Or the covalent bond consists of 2 electrons. What if both of them just happen to be a little bit closer to one for an instant before they swing over to be on the other side? Well, if they're more on one side, let's say on the right side, there's a temporary or, partially negative charge there as the electrons end up on one side just for an instant. And then for the instant, then the other bromine is shy of a few, short of a few electrons, so it'll be slightly positive. And if this bromine molecule is in a collection of other bromine molecules, well then, and they're all kind of stuck together, nearby bromine molecules are going to feel that positive and negative charge for just an instant and cause that molecule to have an induced dipole. So if another bromine molecule is close by and this bromine atom is slightly negative, it's going to repel some electrons from the neighboring bromine molecule, push them to the other side away, and then the nearby bromine atom will have a slight positive charge. And wait, that nearby molecule has a slight positive charge, and this one has a negative charge at this end. Opposites attract, and they'll pull those two together. Van der Waals forces, London dispersion. Okay, so that's what's going to happen here in this reaction. Same idea. At some moment in time, maybe the bonding electrons are slightly more to the right. So just for an instant, the bromine atom on the left is slightly positive. At the same instant, this alkene collides with it, right? So these two molecules are in solutions, bouncing around, and we have this cool effect where, for an instant, there's a temporary or an induced dipole here. Bromine on the left is slightly positive, and the lone pair says, whoa, look at that positive charge. Let's go bond with that. And that begins our mechanism. Wait, bromine is a halide, hunk, H-O-N-C, H, first letter, one bond. That's a quick little way to remember how many bonds do the halides usually make? One. So if the lone pair is going to connect this bromine, that's going to be a new bond, one and only bond to the halide. This bond then has to break off, otherwise this first bromine would have two bonds. There we go, two curved arrows in the first step of the mechanism. And then we get this intermediate where, well, nothing happened to the cyclopentane ring, so it's still there. Pi bond's gone, methyl group's there. Ooh, let's not put that methyl group in just yet. So I gotta remember to add the methyl group. So now which carbon atom does this bromine attach to? Trick question. It attaches to both. And let's say that the bromine and the cyclopentane ring collided such that you're looking down on the ring and the bromine actually is coming up towards you as it connects to both ring carbons. So we'll put a pair of wedge bonds here and connect the bromine there. Okay, and just a minute ago I said, wait, halides only bond one time. Usually only bond one time. It's possible to get the halide to bond twice. It's unusual, and when that happens, they usually carry a charge. And it turns out bromine has a +1 charge when it makes two bonds. Okay, we get this cyclic intermediate, three-membered ring, three-atom ring, a triangle. However you want to name it, that's a key intermediate. You have to draw that on exams when I ask for a mechanism. It's important. Alrighty, so the bromine is coming out towards us. This ring carbon on the left is sp3 hybridized. Now if the bromine is on a wedge, the other group must be on a dash bond. Okay, so I want you to realize that the methyl group was attached to an sp2 hybridized carbon. What's the shape of sp2? Trigonal planar, flat triangle. Flat is the key word here. So this methyl group is not on a wedge, not on a dash, it's flat with the rest of the ring. Okay, however, when the bromine made that new bond and changed this carbon from a double bonded carbon to a single bonded, the carbon went from sp2 to sp3 hybridization. 4 bonds to the carbon. Methyl group, you can't stay flat anymore because that's the wrong shape of sp3. sp3 is tetrahedral. And so the methyl group in this case is pushed down. And then to complete the intermediates here, we start with 2 bromine atoms. One attaches the ring, the other one gets kicked out as Br-. And I am going to draw in the lone pairs because I need to start my next curved arrow on a source of electrons. Over here in the margin, that's not the margin, over here out of the way, we also have to realize that the bromine could have come in from the bottom of the ring. Doesn't have to come in from the top. So it's possible the bromine could be attached to the bottom through a pair of dash bonds, still positively charged. If the bromine's at the bottom dash, that pushes the methyl group from the flat position of where it used to be. Bromine comes up from the bottom and shoves the methyl group upwards towards us. So we also get that intermediate. What's the relationship between these two intermediates? Well, we're just switching dash and wedge bonds. We switched them all. That's a pair of enantiomers. Yeah, we have two chirality centers, and these are enantiomers. See how that all comes together from unit 1? Yikes. Chemistry just builds on itself. Okay, take a little break there, kind of let it flow. We got it all together. We're halfway through the mechanism. What's the next step? Well, this Br minus is attracted to Br plus. Yeah, and if the two bromines collide, the reaction reverses. Everything just undoes itself. We go back to an alkene. Not so interesting. The other thing that can happen is that the carbons of the ring are building up slight positive charge. Why is that? Two reasons. Who's more electronegative, bromine or carbon? Darn, where's my periodic table? Well, trust me, carbon is farther away from fluorine. Bromine is closer to fluorine. And the trend is the closer you are to fluorine on the periodic table, the more electronegative you are. You can also look up a table of electronegativities, and bromine is more electronegative. So, being more electronegative, the electrons in the wedge bonds, electronegativity means those bonding electrons are drawn towards the more electronegative atom, and that creates slight positive charges on these carbons. Just because the bonding electrons don't spend an equal amount of time nearby those carbons. That's reason number 1, the difference in electronegativity. Reason number 2 is bromine's positively charged here. These bonding electrons are just naturally attracted to that positive charge. Dang. So that's starting to increase the positive charges. If these bonds were to break, and they don't, but if they would, then the carbons of the ring would be left with 3 bonds and a full positive charge. They would be carbocations. And that's the thing to realize here. They're not becoming carbocations, because if they did, we might have a rearrangement. Yeah, check out the last videos. Darn it, the last video. Whenever we have a carbocation, there is a chance for rearrangement, which gives extra products, which you have to write down and draw on the exam. Yikes, more to remember. Thankfully, nope, we do not get a carbocation here, but it's starting to appear as if it could, and that's the thing to note. The carbons are building up positive charge, and then they kind of behave similarly to a carbocation, meaning that, do you remember the trend of stabilities of carbocations? Who's more stable, a tertiary carbocation or a primary carbocation? Tertiary. The idea is that a tertiary carbon has 3 attached carbons, and those carbons would be bonded to other things, and bonds are electrons. So a tertiary carbocation has some neighboring carbons who have electrons that can share them a little bit and help partially neutralize that positive charge of the carbocation. Whereas a primary carbon only has 1 carbon group with electrons, doesn't get much help, more reactive, more unstable, not so good. So what we have here, let's identify the degree, let's classify the carbons here of the ring. That's what I want to say. So hey, carbon on the left, you have slight positive charge. What degree are you? How many carbons are you attached to? This carbon says, well, I see the methyl, I see the ring carbon up above me, and I see a ring carbon to my right. There's 3 carbons attached. I am tertiary. So I'll put a little degree 3 here, meaning the carbon of the 3-member ring on the left is 3rd degree tertiary. Hey, carbon on the right, what degree are you? I only have the 2 attached ring carbons. I'm secondary. Put it over here. Cool. Okay. What's more stable, a tertiary carbocation or a secondary carbocation? Tertiary. So what's going to happen in this 3-member ring? It's not a tertiary carbocation, but it can stabilize partial charge just like a tertiary carbocation could. And that allows this carbon, the tertiary one, to release the electrons more than the secondary. The bonding electrons, that wedge, those electrons actually can travel closer to the bromine because this carbon can deal with the positive charge that builds up as those bonding electrons move closer to the bromine. And that charge difference is significant, meaning that this bromine can feel that and it'll attack the other side over here and come in from the bottom. So this positively charged carbon, slightly positive, but more positive charge than the one on the right, the tertiary carbon, has a greater positive charge, attracts the negative bromine. And so one of the lone pairs, start my curve down on a lone pair, is going to be used to attach the bromine to the bottom of the ring, side opposite the big fat bromine up above the ring in this three-membered ring. Okay, but carbon can only make 4 bonds. So incoming bromine makes a new bond. The bromine that there is the outgoing one. This wedge on the left has to break. The wedge bond on the right stays put. So let's draw that one in first. So nothing happened to the ring carbons. Those 5 are still attached. The wedge on the left broke, but the wedge on the right remains. Wedge on the right remains. Cool. Bromine, that was negative, came in from the side opposite the three-membered ring bromine. The three-membered ring bromine was towards us, so the bromine that comes in has to approach from the side opposite on a dash bond. Wait, the methyl group was on the dash. Yeah, so too bad I don't have a nice model, and we could see this three-dimensionally. As the bromine comes in from the backside, the dash bond here that holds the methyl, those are electrons, right? Bonds are made up of 2 shared electrons. Those electrons will be repelled by the negatively charged bromine and get shoved towards us. So the bond doesn't break, it just gets moved towards us. So the methyl group used to be away from us on dash, but it got pushed upward by this new bottom bromine such that the methyl group ends up on a wedge. Yay. And that's our product. And it's an addition reaction, so there's no other atoms left over. The atoms of Br2 added to the organic molecule, the alkene. Yay, we're done. If you wanted to continue with the enantiomer, how does this bromine anion attack? Same pattern. Who's carrying more positive charge? The ring carbon on the left or the ring carbon on the right? Well, classify them first. The ring carbon on the left is tertiary. The ring carbon on the right is secondary. Tertiary carbocation is more stable. So the bromine comes and attacks this tertiary one over here. So I'll put a slight positive charge, maybe a double plus to remind us that's more positive. And then because of sterics, which is a fancy word for crowding, this time the bromine's beyond the ring on the other side. So hey, Br minus, don't come in from that side. It's too crowded over there. Come in from the top. So the incoming bromine hits the tertiary one, but from the top. Hey, the methyl group's in the way. Yeah, just push that to the other side so that methyl, now you're on a dash. And the incoming Br minus attaches at the top on a wedge. So that's the top view, top facing bond. And then this bond had to break, right? So I already got 4 bonds to this carbon. So this bromine of the 3-member ring, that bond, that dash bond on the left has to break. So another curved arrow to show that. The dash bond on the right, though, remains intact. And so the other bromine stays there. There's our product, the other enantiomer. On the exam, I'll only ask you to draw the mechanism for one enantiomer, because the other one looks exactly the same except for a switching of the dash and wedge bonds. What else do we need to do? You can never get Br2 or Cl2 to add to a ring, a cyclohexane ring, so that the halides end cis. Nope, because of the mechanism, and it's right here in the mechanism, where one bromine attacks the side opposite because of crowding, sterics. That forces the product to always be trans. The two identical groups, bromines, one's wedge, one's dash. And that happened here too. Identical groups are bromine, and they're on one dash, one wedge. These are trans. The chemists would say that you get anti-addition. It's a fancy word. Don't get too mathematical because it sounds like subtraction if it's opposite addition. Sorry, bad pun. It's anti, side opposite. Anti referring back to our Newman projections. Oh man, all this stuff building up, right? The anti-conformation is the most stable, Newman, where the biggest groups are opposite. And that's what's happening here. The identical groups are opposite. That's what's anti, and we had an addition reaction. That was a quick little review. I don't know how quick it was, but it was important because everything we did here, piecewise, is going to show up in today's additional reactions. Okay, enough of the review. Let's on with the new stuff. Okay, little tweaks at a time. What we're going to do first, I imagine what happened first, is that someone got sloppy in the lab. I was doing this reaction. Let's stick with bromine. And what do I want to do? Let's do the same thing. Let's say that might be helpful. Let's say someone heard about this reaction, or maybe it got published, and they say, yeah, I want to do this reaction too. But this chemist was sloppy. And by sloppy meaning didn't have pure reagents, or maybe they didn't dry their glassware. And either the reagents had a little bit of water in there, maybe they left the lid open and the humid air kind of deposited some water inside the reagents, or the round bottom flask they're using had some water in it. Water got into the system somehow. And you know what? A little serendipity, that actually formed a brand new reaction that is quite useful. We call it halohydrins from alkenes, this reaction. And you can break down this new word, halohydrin, into halo, which refers to a halide or halogen. And the hydrin part refers to hydration, or just, if you hydrate yourself, you get some water. And organic chemistry, the water group, if you put an OH group, oftentimes that comes from water. So what we're going to get is a halide with an alcohol where there used to be a carbon-carbon double bond, where there used to be an alkene. And what's beautiful about this is it's very, very similar to the reaction we just did, halogenation of alkenes. So if you know that reaction really well, the mechanism really well, just apply that here. Another key point, some textbooks point out that if you want to predict where things are going to go, pretend the halide is a hydrogen and use my Markovnikov rule. That'll predict where the halide goes. More on that in a minute. Because the mechanism is very similar to halogenation of alkenes, and that halogenation reaction goes through anti-addition, so does this one. So that means the new groups, the halide and the alcohol, they're going to be trans to each other on a ring. Oh, that's the next point. So you always get anti-addition, even if you have a chain. But sometimes, because it's not a ring, the chain after the reaction can actually spin, and in one shape, may the halide and alcohol appear to be on the same side. And they can spin to be on opposite sides. The ring, however, keeps the two groups, the halide and the alcohol, on opposite sides. Another word for anti-addition is the reaction occurs with anti-stereochemistry. And yep, there's a mechanism, nicely though. As long as you know the first mechanism we just reviewed, halogenation of alkenes, you got the mechanism. Beautiful. So let's just crank it out. Let's start with 1-methylcyclopentene. Previous video, we talked about how to name this. And actually, I may at the top here, let's show the overall reaction. That can be a good strategy on exams. So if we're going to ask for the mechanism, reaction mechanism, you might want to just predict what the final products are going to be. That's your target. That's what's the molecule that you need to show forms from the mechanism. So it's a good strategy. And then you can use the same reagents you had in halogenation. You can use chlorine or bromine. And again, iodide, too stable, doesn't work well. Fluorine, too reactive. It's hard to make it and keep it in a container because it reacts with it. But you also need water. Like I said, I imagine someone was a little sloppy, introduced some water, and it turned out to be a good thing. It made a new reaction. Okay, so let's pick bromine again so we can compare it to the reaction we just did a minute ago. And now you also have water. And whether the water or the bromine is on the top, doesn't matter. You just put the reagents above or below. And what happens? Well, one bromine goes to one alkene carbon, and an alcohol from water goes to the other one. And you lose the pi bond. Okay, what about the methyl group? Well, it's going to be pushed to one side or the other, as is sp2 carbon goes sp3. What else do we know? The bromine and the alcohol are going to add by anti-addition. They'll be trans to each other. Cool. But who's paired up with the methyl, the bromine, or the water? Well, that's where Markovnikov's rule will help. If we're going to just do hydration, I don't know if I introduced that in the previous video, but if you just add water and an acid, that reacts all by itself with an alkene by Markovnikov's rule that says, okay, hydrogen of the reagent goes to the carbon, alkene carbon with more hydrogens. That's this one. This carbon on the right has a hydrogen. The other alkene carbon doesn't. Same rule apply for HCl, adding to a double bond. HBr, HI, Ki with H3PO4, phosphoric acid, and dilute acid, water. Hydrogen would go here from the alcohol. Okay, the little trick here to remember is the halide kind of acts like the hydrogen. The bromine is going to go on the right. And yeah, it's going to create a chirality center here. There'll be a hydrogen, a bromine attached on the right, and then there'll be this carbon of the ring is different from this carbon ring. So that is a new chirality center. But you're going to get enantiomers. Sometimes the bromine's on a wedge, sometimes on a dash. So you can just write a plain bond and know that this is going to be a chirality center. And if it's just an ordinary bond, well, which one is it, wedge or dash? You get both. So nice quick drawing. It's going to be either one. And then over here, ooh, I might change my idea, my idea. Over here, we need the alcohol to be trans to that. Darn it. So now I need to pick. To be trans, we need one alcohol. We need the alcohol to either be dash or wedge, and the bromine to be the opposite. So maybe I'll pick the bromine to be a wedge, and then I'll make the alcohol a dash. And then I put the alcohol on a dash to make it trans, which forces the methyl group. How about if I write CH3 like it did before? This is sp3. If I already have a dash bond here, I must have a wedge, and that's a methyl. And then hopefully some of you are saying, wait, what happens if the bromine is not on the wedge? Well, then you get the enantiomer. Bromine will be on a dash bond, meaning trans to that will be the alcohol. That's anti-addition, making the alcohol and the halide opposite sides. And now the methyl group just gets shoved to the side opposite the alcohol. So alcohol was towards us, methyl group, you gotta go down and away on the dash. We predicted the products. Now let's show how both of these, yeah, I'll do both. On the exam, you only have to show how one is formed through the reaction mechanism. And the nice thing is, as long as you know the other reaction, you got this. So let's do this mechanism, this pattern again. Too bad they both can't stay on the page at the same time, on the screen that is. So instead of writing Br2, let's show that covalent bond. And the first thing that happened is pi electrons attached to this bromine, kick out the other bromine. If you want to put in the lone pairs, you can. You don't need them because my curved arrows don't start on them. So you can choose to leave them out. And now we're going to form that three-membered ring, and I have to choose. So maybe I'm going to make this first product with bromine. It's going to be on a wedge bond, so I'm going to choose wedge bonds. But you could have chose dash, and then you'd be making the product on the right. Three-membered ring, bromine there, plus charge. Where's my methyl? Well, it was sp2 flat. This bromine came in from the top and shoved the methyl down below. And there's our intermediate. Nice. We also make a Br minus. I'll put it up here. Hey, but the sloppy chemists allowed some water to enter into this reaction. It turns out there's usually more water than Br2. So by concentration, there's more water molecules, higher concentration, and the kinetics would mean that the water would react more often because there's more of it. Just statistically, water can collide with this molecule and react more often than a Br minus can react. Also, the nature or the property or just the intrinsic reality of these things, turns out water is a better seeker of positive charge. Seeker of positive, a better nucleophile. So water is more nucleophilic than Br minus. So 2 reasons why the water is going to attack rather than Br minus. If Br minus attacked, we would just be repeating this reaction. See, right there, Br minus attacking. But there's more water, water's more nucleophilic. Water wins the race to this 3-membered ring. And again, same reasoning, which carbon of the ring does water want attacked? The tertiary one, because it bears more positive charge than the secondary one. Squeeze that in here. Tertiary carbocations are more stable than secondary, so it's not a full carbocation, but it builds up charge like a carbocation, and there's more of it on the left side because it's tertiary. So water is drawn into this, but it's going to approach from the side opposite the 3-membered ring. So this crowded triangle with bond angles of 60, it's really, strained and ready to pop open. Just needs a little help, and here comes the help. Water comes in from the side opposite. It's going to push the methyl group up. Carbon lets go of the wedge bond, saying, yay, here's my 4th bond, the water. See you later, bromine. And the bromine stays attached on this wedge and swings over to the other side. Swings over to the other side. Cool. The methyl group got shoved upward, so now it's on a wedge. Water attacked from the bottom. How did it attach? It used its lone pair. What about these H's? They're still there. There's no curved arrows associated with the 2 hydrogens to say that there's any change. There is no change. In this step, hydrogens just went along for the ride. Oxygen just said, hey, I'm going to use this lone pair on top, attached to the bottom of the ring, and we're good. And then it had second thoughts. Wait, oxygen, how many bonds are you making? It's making 3. The 2 H's plus the bond to the ring. Wait, how many bonds are you supposed to make? HONC. 1, 2, 3, 4. Wait, 2. Oxygen, you're not bonding normally. Nope, it's not. It has slight positive charge. Not slight, full positive charge. We're not done with the mechanism yet. You need to clean this up. The product is supposed to be this one here. Okay, and as you look at the drawing of this one, compared to what I have drawn, it's not exact, but they are the same molecules, right? Methyl group on wedge, alcohol on dash, well, what will be an alcohol on the dash, and on the right side, bromine on wedge. They're the same molecules. Wait, what do I have to do to make this alcohol? I have to end up with an OH when I have 2 H's. I gotta get rid of an H. And I also have to end up with oxygen with a neutral charge. So I have to get rid of the plus. So what we have to do is remove an H. There's 2 H's. The product only wants 1, so you remove that H, and you have to remove that plus. You have to remove H plus. What's H plus? That's an acid. So you need a base. That's how I kind of reason it out. I need to bring in a base to remove this H plus, so I can create the final product, which I can draw, because after this hydrogen leaves, the methyl stays where it's at. But what used to be, I guess you could call this like a hydronium ion. It looks like H3O plus, but it's H2O plus with a carbon. It's going to turn into an alcohol group. All right, so what base? Sodium hydroxide? No. Did you add any sodium hydroxide? No, you didn't. You added Br2 with water. Those are your choices. And the organic molecule is not a base. You did make some Br minus. Negative things oftentimes are basic. But back in Gen Chem, you might remember that when you add the halides to water, the pH does not change. Right? So if you add sodium chloride, table salt, to pH 7 water, it stays pH 7. Those chlorides do not grab H pluses from the water and create, you know, a base. That doesn't raise the pH. Neither does Br minus. Br minus is not a base. What about water? Yeah, back in general chemistry, we talked about equilibrium reactions. Water was always a weak acid or a weak base. You can do either one. That's our only base available to us. So water serves as the base that's going to go use its lone pair. It's a Lewis base, lone pair donor. Go grab one of those H's. And you know what? I'm not a stickler for this amount of detail. Technically, one of the one and only bond to the hydrogen attached to this oxygen, that needs a break. But if you don't draw on that curved arrow, I'm not going to take away 8 points. This is good. What became of the water molecule as it picked up H plus? It became the hydronium ion. Now we're done with the mechanism. And this video is getting a little long, so I am not going to show the mechanism of how to make the second one, but it's going to look exactly the same. Just in the first step here, instead of having the bromine on 2 wedges, they'll be on dashes. Cool. I think we're good. What else do we need to say here? Oh, little detail here. You can use the word trans to describe the positions of the alcohol and the bromine, right? So what's the relationship between the alcohol and the halide? Are they cis or trans to each other? Well, the alcohol's on a dash, halide's on a wedge. Ooh, they're trans to each other. However, if you need to name this, you cannot use the word trans in your name. When you use the word cis or trans in a name, it says, how are the 2 identical groups related? And an alcohol and halide are not identical. So you can't use the name. Did I name this? I did. And so if you want a name, I believe the name would be 1R, 2R, 2-bromo, 1-methyl, cyclohex, oh, cyclopent, 5 carbons in that ring, pentanol. Okay, now I'm not going to show how to name this because we're getting ahead of ourselves. We haven't discussed how to name alcohol groups yet, but when we do, we're going to use the suffix OL. And the most important functional group is the alcohol in this molecule, so it's forced to be on carbon 1 of the ring. So that's the only place you can put it, so you don't have to put a 1 next to the suffix. I can't use cis or trans here because there are no 2 identical groups that are wedged, both dash. There's the unwritten hydrogen here, but that's different from the others. In fact, because they're different, these are chirality centers, and that's how you have to describe how the alcohol and the bromine are opposite each other, is through the use of the assigning the configurations R and S. Cool. So outside of class, maybe the office hours, if you need to figure out how to do, if you don't see how to do R and S, I can show you how to do it here. Or you can just check your answers if you do recall how to do it. We're done with halohydrins. Let me just check my notes. Still anti-addition, right? Did I say that? I hope I did. Right here, the water attacked side opposite the halide, the ring. That is where anti-addition takes place. That results in the alcohol and the halide being trans to each other on the ring. Nice. 1 done. 2 more to go. Next reaction. We actually already saw this before, but I thought, you know what? We'll just go over it again. So in the previous video, electrophilic addition of alkenes, one of our reagents was the hydronium ion. And hydronium is formed when H plus reacts with water. HOH, that's a weird way of writing water, but there you go. It is water. You can also write the reagents as H2SO4 reacting in a mixture with water. You can put the water on top, sulfuric acid on the bottom. So any variation of these three sets of reagents will transform an alkene into an alcohol. So the reaction was discussed earlier when we did HCl, HBr, HI, and the other reagents that make hydroiodic acid was Ki with, maybe I should put a slash or something, with phosphoric acid. And then we said you can also use dilute acids. And the arrows could represent dilute acid in one of these three ways. So take a look at that previous video for the mechanism and the discussion of Markovnikov's rule. The key thing here is that you get carbocations that can rearrange. So I have to watch out for that. Memorize the mechanism. So I didn't show the mechanism specifically for hydronium ion reacting. We did the mechanism, I think, for HCl. So I thought I just, as a review for the mechanism, because it is the same as HCl, except it has one extra step at the end, I would just go ahead and do it for water with dilute acid reacting with an alkene. Cool. Before I move on though, this is a great reaction for taking alkenes and making alcohol groups out of them. The big limitation, however, is that you make carbocations. Carbocations are prone to rearrange. They don't always rearrange, but when they do, you get extra products that you have to then in the lab separate one product away from the other, and then you get mixtures that reduce your overall yield for one of them. It's not an ideal situation. Okay, so let's look at the mechanism. And which am I going to do? Let's just do the one on the screen. We got propane there, so I'm going to draw the skeletal drawing of it. And then we have H plus. Let's actually draw it as H3O plus. Your choice. When you're doing the mechanism, drawing molecules, you decide which form of your reagent you want. I'll pick hydrogen. It's kind of cool. It's very similar to the two mechanisms we already saw in this video. Lone pair, not lone pair, pi bond, pi electrons. Go grab an H plus before it was a Br with a delta plus. Same idea. I'm being a little loose. It's okay on exams too. There is a bond for the hydrogen to the oxygen. Another curved arrow there. You don't have to show it though. So there's the Lewis dot structure of hydronium. When the pi electrons grab H plus, this bond breaks, returns these bonding electrons to oxygen as a second lone pair for water. But up here it's fine, just one curved arrow, totally fine. The hydrogen is going to go to one of these carbons. Unlike the halides, which can make two bonds, hydrogen cannot. So hydrogen, you pick. You want to go to this carbon or that one? Well, nature decides. When the hydrogen goes to the end of the chain, we get a secondary carbocation forming and not a primary. So if the hydrogen were to go to the middle alkene carbon, then that would place the positive charge. The carbon that still misses a bond, that carbocation would be at the end. That's primary, which is more reactive, more unstable than a secondary carbocation. And you know what? Why don't we have a little review and let's get a carbocation to rearrange. Let's add a couple more groups here. Let's make this, yeah. So what do we got here? So this carbon here, I'm gonna bend the chain that way. I'm drawing it, I get to change it. Well, okay, so what do I have? I have, let's count from this end. That's how we would name it. There's one carbon here, 2, 3, 4, 5, and in the middle there's an ethyl branch. So starting here, 1, 2, 3, 4, 5, and there's an ethyl branch. Yeah, they're the same. Okay, that's first step. As hydronium releases H+, you create a water molecule. Water molecule can, in some cases, well, just statistically, right? So we're not doing this reaction with just 2 molecules, 1 hydronium ion and 1 alkene, right? We got Avogadro's number of molecules in our beaker, in our flask. So sometimes, as a reaction occurs, the water is just right there and attacks immediately. Lone pair on the water molecule can give that carbon its 4th bond. So the water molecule attaches. Oh wait, the oxygen just added a 3rd bond, it's positive again. And then we have these 2 ethyl groups. That's all right, kind of visualizing. From this carbon, there's an ethyl up and an ethyl down. Cool. However, sometimes though, instead of the water immediately attacking, the water's like bouncing around solution, not getting over here this positive charge in time. And the carbocation's like, dang it. This carbon's like, where's my 4th bond? And this carbon over here is tertiary with a hydrogen, says, here, borrow my hydrogen for a while. So there's an alternate mechanism. And you need both on the exam. Well, yep, both, because you have to explain how 2 products form in this reaction. So let's just copy this intermediate, because sometimes the water molecule attacks carbocation directly. Other times it's delayed, doesn't get there. And this hydrogen will attack the carbocation. Call that a hydride shift. Carbocation, it's one type of carbocation rearrangement. That's a carbocation rearrangement. The hydrogen slides over. Really, it's the bonding electrons. These electrons just say, whoa, there's a positive charge over there. Let's go there. And the hydrogen remains attached to those electrons as they slide over. And then when you're drawing it, you decide how you want to draw it. I'm going to put the hydrogen up on the mountain peak. And now this carbon, which used to have the hydrogen left. This carbon only has 3 bonds. Now it's a carbocation, but it's tertiary. And that's more stable than the secondary carbocation. That's why the rearrangement occurs, to make a more stable carbocation. So now this intermediate can sit around and wait for the water molecule to show up and do this step up here. Give that carbon its 4th bond. And so if you want to come in from this side or that side, I'm going over the top. However you want to do it. The water attacks and adds, using its lone pair, dragged the 2 attached hydrogens in this next step in the mechanism. And at some point, if you care not to put in these hydrogens and just go pure skeletal drawing, you can. All right, but we don't have the final product yet. The oxygen atoms have 3 bonds. They should have 2. I'm going to give them 2 bonds. So let's remove an H. Oh, and a plus. Let's remove H+. Hey, we saw that before. How do you remove H+? You need a base. So what bases do I have in my reaction? I don't have any. Yuck. My reaction started with an alkene and hydronium. That's all I had. That's all we have. Where's the base? Well, you have to break down hydronium. H+ and water make the hydronium ion. You can think of it as equilibrium. And the H+ got donated to the alkene here. We actually made some water. What else do we know? If you put some sulfuric acid, so here's a 3rd way to make hydronium. If you put some sulfuric acid in water, every single molecule of water does not receive H+. This is a dilute solution. So maybe we put a few drops of sulfuric acid into a beaker of water, And all the sulfuric acid releases at least one H plus, but there's not enough H pluses, even if both H's were released from a few drops of sulfuric, there wouldn't be enough H plus to give every water molecule an H plus. What I'm trying to say here is, yeah, you can think about this equilibrium supplying water, but probably there's extra solvent, extra water. They're just swimming around solution, and that is your base again. So both times for top mechanism and the bottom mechanism, you just get some more water from the solvent. That's going to serve as a base. So remove this extra hydrogen and make our product. So you get an alcohol. That's the product of this hydration reaction. And then the water molecule became H plus. Sorry, attached an H plus become hydronium ion. And you got the same pattern over here. Go down below just by choice. You could start on the curve here on the top lone pair and go over across if you like keeping things the same. Or a little variety, this works too, but water molecule, go grab the H plus, make some hydronium ion, and make the final product, which is an alcohol. Cool. What degree is this alcohol? Well, the oxygen's shy, so talk to the carbon. Hey, carbon, what degree are you? Attach the carbon up here on top left, top right, and the bottom hydrogen. There's 3. I'm a tertiary carbon, making that a tertiary alcohol. Hey, what degree are you, alcohol? It's shy. Talk to the carbon. Hey, carbon, what degree are you? I got carbon on my left and on my right. I'm secondary, making that a secondary alcohol. You need both of those on exam. Ooh, and you'll miss a half a point. I know, all these details. What became of the water molecule? It turned into hydronium. We're done with the mechanism. And yeah, you need both of them because you get both products with this rearrangement. Yeah, I don't like it either. So let's do a different reaction that doesn't make carbocations. So no multiple products. But we're going to need a new set of reagents to do that. Let's see, before we move on to the next reaction, one little minor point. Over here on the far left of the screen, you can see that we started, let me scroll over so you actually can see that. We began the reaction with hydronium ion, dilute acid. Hydronium ion reacted with an alkene, and then it turned into water, and then later, a water molecule grabbed H plus and reformed hydronium. So how many hydronium ions were used up in this reaction? Well, you used one here and you made one here. There's no net change. You didn't use up any in the course of the mechanism. Sure, it reacted, but the number of these, the concentration, is not going to change. This acid is a catalyst. It's a catalyst that did not get used up, and it sped up the reaction. So be aware of that. This satisfies the definition of catalyst, even though I know some students saying, wait, I didn't think catalysts react. Well, if they don't get reformed by the end of the reaction, then they're not catalysts. But yeah, catalysts do a reaction, can react. As long as you don't use them up by the end of this reaction sequence, the reaction mechanism, they can be catalysts. Cool. All right. Where's the next reaction? It might be at the top. Yep, we started here. Seen a bunch of reactions today. Oxymercuration and demercuration, that's the next one. So, just like you, there's scientists who don't like those carbocation rearrangements. And they don't like them for different reasons. The reason is they create multiple products, which you then have to go through extra work and expense to separate one product from the other product. And 2, your yield of one of those things just decreased because some of the reagents were used to make the other. And then 3, what are you gonna do with the waste product you don't want? Well, you have to think of waste disposal and its effect on the environment. So not a good idea. So even though dilute acid is so readily available, it causes carbocations to rearrange. So we usually do not pick that reaction, usually. Instead, let's do this reaction, oxymercuration, demercuration. Where are these crazy words coming from? Oxymercuration. So we saw halogenation. That's where you add halides. Now we're adding oxygen and mercury to what? To an alkene. And then later we're going to take away the mercury, so detach it or demercuration. Yeah, this is actually two reactions. What we're going to do is, let's start with propane. First reaction is we're going to add mercury in the form of a mercury salt with acetate. Why don't I draw it this way? Let's draw skeletal drawings for acetate. You would know it better from Gen Chem as this polyatomic ion, C2H3O2, or maybe CH3COO. They all work. The organic chemist likes to abbreviate acetate as AC, which is a horrible acronym, horrible abbreviation, because there is an element on the periodic table, actinium, that's easily confused. Sorry about that. So in the lab, if you have to calculate the formula weight, the molar mass of mercury acetate, and they write this AC, don't use element AC. You have to remember that's the chemist abbreviating acetate, and the chemical formula is C2H3O2 when you see this OAC. Sorry, that's not so fun. There's two of them, so drawing two acetates. There we go. So you mix in this mercury salt, mercury acetate, one of those three. You can also draw it in this one of these three ways. The most common way is actually this way. And then you have to add some water, because this whole purpose was to make an alcohol like we did with hydronium ions. So you need the O and the H to make the alcohol. That comes from water. And then we need a co-solvent. Sorry, I got this one here. I didn't want that right now. A co-solvent, a co-whatty. So who flies a plane? A pilot and a co-pilot. There's two of them flying the plane. So who dissolves stuff in this reaction? We have the solvent water and a co-solvent, THF. THF. Okay, so for now, you do need to know that THF stands for tetrahydrofuran. So there's a T, the H, and the F. You also should know the structure. It looks like a pentagon with one carbon replaced by an oxygen. It's an ether. Ooh, yeah, still know your functional groups. And it's a ether in a ring, so a cyclic ether, if you will. And it's your co-solvent. So why do you need this? It's not going to show up in your mechanism. It's just there to help things dissolve. Because if things don't dissolve each other, they can't collide. And a collision is what you need to get a reaction between two molecules. So a quick little sideline on why THF is necessary. You definitely need a water molecule because that's going to supply the OH, the alcohol group. So is propane soluble in water? Remember the adage, like dissolves like. So if two molecules are alike in their intermolecular forces, they probably will dissolve in each other. Which intermolecular force most important for water? Hydrogen bonding. Which intermolecular force is important for propane? Well, can't do hydrogen bonding. No NH, OH, or FH bond. Can it do dipole-dipole? No. There's no difference in electronegativity to make a polar covalent bond. This one can only do London dispersion or van der Waals. It's completely nonpolar. Nonpolar molecules are greasy in the real world. So we got water, which is polar, and a greasy non-polar molecule. They don't mix. THF, however, has a polar covalent bond on the left, polar covalent bond on the right, and a net dipole pointing up. This is a polar molecule. Water is also polar. Right? There's a difference in electronegativity between oxygen and hydrogen. Net dipole pointing up. Dipole-dipole forces can dissolve THF with water. So these two dissolve in each other. Nice. The bottom portion of THF consists only of C's and H's. So the bottom half is actually a non-polar region of the molecule. So this end of the molecule can stick through this molecule through London dispersion or van der Waals forces. And so THF helps bring the water molecule sticking at the top of THF to contact the alkene, which is sticking to the bottom of THF. Cool. Later in this course, maybe next semester, we'll talk about soaps and the kind of similar phenomenon that happens there too. THF is not a soap though. Anyways, moving on. That's the purpose of THF. It's going to help dissolve things together. No T, no H, no F shows up in product. It's just a solvent. Required on exams. You get the job done, but it doesn't show up in the mechanism or on the products. The mercury, however, is not a catalyst, but it does end up in the product. Well, the final product anyways, because they're just trying to make an alcohol. After this first reaction, mercury, THF, and water, you get a product, which I'll draw later, but it contains mercury, Hg. And so then the second reaction is going to get rid of it, detach it or demercurate, demercuration. And the reagent is NaBH4, also known as sodium borohydride. Think of it as a source of hydride ions. And so what's going to happen is H- is going to kick out an Hg, a mercury atom. So this is going to be a one-to-one switch substitution. And then you're going to get a alcohol. That's what we wanted. So hydration of alkenes was where we took, sorry, my screen's getting a little funny here. Move this out of the way. It's where we took, let's take propane. And we took hydronium or some other form of hydronium as a reagent, H2SO4 with water, and we added an alcohol. And it was Markovnikov's addition, right? The rich gets richer, meaning the H of the reagent goes to the carbon with more H's. Yeah, this one had 2, this only has 1 H. The rich gets richer. Or the hydrogen of the reagent goes to the alkene carbon with more hydrogens. But we also saw carbocation, Cc+, rearrangements. Propane can't rearrange, so that's kind of nice. You don't always get a rearrangement, but sometimes you do, like we did in the previous example. If you want to avoid rearrangements and still make an alcohol using Markovnikov addition, switch your reagents to these sets. Oxymercuration followed by demercuration will take propane and convert it into the exact same alcohol without producing a carbocation, so there's no chance of rearrangements no matter what kind of alkene you use. Okay, there's another way to write all this a little more quickly. This set of reactions always occurs in this order: mercury, salt, water, THF, followed by sodium borohydride. So if you want to take less room on your sheet of paper or on the exam, you could put a little 1 in front saying, hey, reaction number 1, mix the mercury 2 acetate with H2O and THF. And in the second step, reaction number 2, add sodium borohydride. And guess what? You get the same exact reaction as hydration of alkenes, which means the rich gets richer. The H of the water goes to the alkene carbon with more hydrogens. This one has 2. This top one only had 1 hydrogen. So the hydrogen of the water goes to the carbon with more hydrogens. And the remaining part of the reagent, the OH group, goes to the other alkene carbon. Done. Nice. Okay, so far we have 2 ways of making the same alcohol from an alkene. One using carbocations and one without. So what's the mechanism here? Well, first let's go over a few key points, which I think I've already outlined here. We're going to use Markovnikov's rule to predict the product. We don't see anti-addition or even its opposite, syn addition. It's a mixture in the lab, so depends on reaction conditions. So if you have a ring with an alkene and we added Br2, the bromines went trans, anti-addition. Don't worry about that here. Oxymercuration, demercuration doesn't have a preference. You get a mixture of cis and trans. Hydration also gets a mixture of cis and trans. And that's because of the carbocation is flat. The alcohol group can come from top or bottom. What else do we know? Oh, that's right. Oxymercuration, demercuration has more things to remember. The THF, the chemical formula of mercury acetate, chemical formula of sodium borohydride, but you avoid carbocation rearrangements. Your yields are higher. You don't have to purify things as much at the end. So this is better. So remember, that'd be your preference on exams. You do have to memorize the mechanism. I'm going to ask for at least 2 mechanisms on your next exam, so this one might be one of them. And then it turns out, if you go to most textbooks, they don't give you the mechanism for the sodium borohydride, the second reaction. And the reason for that is, if you know the mechanism for the first reaction, you've already correctly predicted where the alcohol group is supposed to go. So the sodium borohydride just removes the mercury. It's not so helpful for predicting products. And that's going to be my guideline too for the entire year of organic chemistry. Every reaction we explore will have a mechanism, but sometimes you don't know the mechanism very well. It's not been well studied. And there'll be other times, well, the mechanism is known, but it's not very useful for helping to predict products. So we will not have to know mechanisms for every reaction we do, just the ones that are helpful for predicting products. All right, let's see that mechanism. And again, it's only for the first one, not for the second one. Only for oxymercuration, not for demercuration. Let's start with propane. And the mercury salt, I'll draw it like this. On the exam, if you care to abbreviate, you can. You can use C2H3O2, whatever. Just have the O's attaching to the mercury. I also recommend going back to the beginning of this video and just memorizing those other reactions first, because we're going to use some details from those reactions to do this one. The patterns are going to repeat. That's cool. So previous mechanisms, we saw the pi bond go and grab an atom, does the same thing here. And then when it grabbed an atom, the other bond, one of these two in this case, has to break. So let's just break away this group. You can break away the bottom one. They're both acetate. They both can be displaced. Now mercury can form 2 bonds. It's doing 2 bonds here. So just like bromine making a 3-membered ring, so does mercury. So there's the pattern repeating. And when bromine was attached up here, it was positively charged, and so is mercury. The difference, though, is that mercury had 2 bonds. Now it's going to have 3. 1 acetate left, but mercury gained 2 bonds. I drew the bottom acetate still attached, so that's the acetate that's over here. Cool. So just like Br2 attacking an alkene, we make a 3-member ring. Nice. And then just like Halohydrin Formation, now we're going to have a water molecule open this up. Open up the 3-membered ring. And we have a choice. Hey, water, do you want to attach this alkene, what used to be an alkene carbon, or the other one? Well, what degree are they? Which one has more positive charge? Which one looks more attractive to the slightly negative oxygen? Well, what degree are you, carbon? I'm attached to mercury. That doesn't count. I got 2 unwritten hydrogen. That doesn't count. There's only 1 carbon I'm attached to. I am primary. Over here, this carbon says mercury, unwritten hydrogen, and more importantly, there's a carbon on the left and a carbon on the right. It's secondary. Now, mercury is farther away on the periodic table than carbon. But I think if we go to the table electronegativities, mercury is a little more electronegative. Guess what I'm saying here is I'm not sure, based on electronegativity, which one is more electronegative. But I do see a positive charge on mercury. And that's going to draw these bonding electrons to the mercury atom and start to build up a slight positive charge on these two carbons. The secondary one can release more positive, can release the electrons more and create more positive charge because secondary carbocations are more stable than primary. We saw that pattern already before. Nice, pattern's repeating. Okay, the secondary, more stable than primary carbocation tells us water is going to attach to the secondary carbon. From which side? Well, the side opposite, but there's a little footnote here. You don't get strict trans products or anti-addition because in the lab, sometimes we don't see complete anti-addition. We get a mixture. On exams, however, you remembered the anti-addition from before, so why don't you just use the same pattern here? Oxygen comes in from side opposite, and this bond breaks. You can draw the curved arrow over here, but it's a little crowded, so I'm going to put it right here. Same idea. This bond of the three-member ring breaks. Mercury's going to take these electrons and quench that positive charge. Water's going to attach to this carbon over here. The mercury is going to stay attached to the primary carbon, though. Mercury's still attached. It's got the acetate. It doesn't have a positive charge because now it only has two bonds. And the water became attached here. Ooh, and now it's positive charge because it has three bonds. We want the alcohol group in our final product. So we have to get rid of one of these H's and the plus. We gotta get rid of H plus. What do we need? We need a base. What base did we use before? We used water before. So you can use water. I will allow that. However, I already missed a half a point. I forgot a detail here. We kicked out this acetate group. That is still floating in solution. That's a stronger base. It's still a weak base, but it's a better base than water. So most likely in the reaction, acetate is going to serve as the base. But you can make a little note. I will permit you to use a water molecule because that might happen too. There might be a higher concentration of water, probably is a higher concentration of water. And so just because of higher concentration, that might speed up the rate of water acting as a base. And the other thing that's kind of nice is we already used water before. So it's a kind of nice pattern to remember to change change an oxygen with a positive charge to an alcohol, add water. And one curved arrow will be enough. Move that H plus. In this case, you can make an argument acetate's going to play the role of the base. And now it forms acetic acid as the conjugate acid. We're done with reaction one. That's all that's required on exams. So that's all for exams. So I know there's still a second reaction, one that's going to remove this mercury. But on an exam, if I ask you for the mechanism for oxymercuration, demercuration, this is all that I will grade. If you go ahead and start doing something with the remaining reaction, like you say, okay, I'm going to take this and add sodium borohydride to it, and you're going to get this molecule where the mercury was replaced by a hydrogen. Awesome. I'll smile and say, nice job. I'm not grading it. It's actually a redox reaction. You can look it up. I haven't seen a full-blown mechanism though, but I've seen more details in case you want to know how NaBH4 reacts with this mercury atom and supplies a hydrogen, but it's not on exams. Check my notes. We got Markovnikov addition in here. Yeah, we did. It's right here. So you don't see the hydrogen go into the alkene carbon with more hydrogens, but that's the net effect And it's because water is attacking the more substituted carbon, secondary versus primary. Mercury ends up on the primary carbon, not the secondary one. And later, mercury gets displaced by hydrogen. And so overall, you get Markovnikov's rule, Mark's rule, being obeyed. The hydrogen does end up on what used to be an alkene carbon that had more hydrogens. Okay, last way to make alcohols from alkenes. So the first way was hydration. Let's take propane, and we add hydronium, and we get an alcohol. And we get the alcohol that's secondary because Markovnikov's rule was followed. The bad thing about this easy, simple reaction is you get carbocation rearrangements. Don't like those. So then someone said, okay, let's do oxymercuration instead. Oxymercuration, demercuration. Same starting material, same product. However, more reagents to remember. Mercury salt with acetate. H2O, THF. If you put them in different order, no points lost. As long as they're all there, we're good. NaBH4 in the second step. If you forget the ones and twos, I overlooked that, but they really should be there. The reason for that is if you don't have a 1 and a 2 here, it implies, hey, in the lab, mix all 4 things together, and then the sodium borohydrate will start reacting with these reagents and cause a side reaction. Not good. So you really do want to do step 1, reaction 1, mix these 3 together, wait till they're done reacting, then add the sodium borohydrate later. Okay, that makes the same secondary alcohol. Following Mark's rule, Markovnikov's rule, but no CC plus, yay, and that's a happy face. And someone else said, yeah, but I don't want to follow Markovnikov's rule, right? There's always some rebel. I want the alcohol at the end of the chain. Hydrogen, go to the other carbon. Can you do that? It took a lot of work. Someone won a Nobel Prize in chemistry for it, Herbert Brown, I believe. But yeah, you can do that now. That's our third way of making alcohols from alkenes. Take propane again, and this time add BH3 with THF. Sometimes you see a dot, sometimes a slash. Put a dot. Check my notes. I put a comma sometimes. That's what's in my notes. And then we add hydrogen peroxide, H2O2, and base. If you just want to write OH minus, totally allowed. It's quite common. Where's the other note? Oh, let's put it in here. Oh, it's right there in front of me. I didn't even see it. Instead of BH3, you can also use diborane, B2H6. And I did have a student come back several years after taking my class. He said, Dennis, tell your students on exams, on the MCAT rather, on the MCAT, I didn't see BH3, I saw B2H6, but because the THF was still there and the hydrogen peroxide and base, I knew it was hydration oxidation. So let your students know. And it may have been the same student who said, you know what? Sometimes instead of this chemical formula of the mercury salt, someone swapped out the hydrogens for fluorine. And it turns out that's a moderate improvement. Trifluoroacetate actually works. The mercury salt, the trifluoroacetate, actually works better. You get higher yields, faster reaction times, I believe. And so MCAP actually used this specific reagent to do the oxymercuration demercuration reaction. Same products though. So just, yeah, that's not nice. So just be aware that they can tweak the reagents, the chemical formulas a little bit, and still refer to the same reaction. Okay, third reaction, last one for this video. BH3 with THF or B2H6. First reaction, wait till it's done. And then afterwards, a second reaction, add a mixture of hydrogen peroxide at high pH, sodium hydroxide added in there. And then you make an alcohol, but this time the alcohol is on the other end of the alkene, the so-called anti-Markovnikov product. So we got Markovnikov's rule, and now we have anti-Markovnikov's rule. Just get the opposite. So you'd say you get the anti-Markovnikov product. The product Markovnikov said you shouldn't get, yeah, but we changed the reagents. So now you can get this one. And high yield too, so very cool. What are some other things? Opposite is opposite. So when we had Br2 reacting with alkenes and rings, we got anti-addition. Okay, borane reacts with double bonds and rings by syn addition, the opposite of anti-addition. Anti-addition, which is same side, or syn addition, symmetrical maybe. Yep. So syn addition or syn stereochemistry, beautifully. Yay, no carbocation, so no rearrangements. Yes, that's nice. Actually, the mechanism is detailed, lengthy, but most textbooks only give you the first step of the first reaction to remember. That's a key step that determines anti-Markovnikov addition and syn addition. And so that's all I'm going to require too. So it's a very short mechanism for us on exams. Let's see, did I leave anything out? It's opposite Markovnikov's rule, anti-Markovnikov's the name for that. Mechanism ends up being syn addition. Same side for the H and the OH. No carbocation rearrangements. Yay! All right, let's see this nice and quick mechanism. There we go. Okay, start with propane again. There we go. And then whether it's diborane, B2H6, or BH3, draw the BH3 molecule so you can see one of the bonds between the boron and the hydrogen. And then think of it this way. Let's classify the alkene carbons. So, hey, alkene carbon on the right, what degree are you? I'm attached to one atom of carbon, so I'm a primary carbon. Yeah, don't use the double bond to double count. Yeah, just how many attached atoms. Hey, carbon, what degree are you? I got a carbon on my left and another one on my right. I'm secondary. Okay, so which one's more crowded, which bulkier? The secondary one. It's got more groups, more carbons on it. It's bulkier, bigger, fatter. I don't know, what word do you want that you remember? It's degree 2. That's my little alarm saying, you're taking too long. We're getting there. We're almost done. This is a quick mechanism. Okay. If you draw a bond between the hydrogen and boron, which I recommend, and then don't draw on the bonds for the two other H's, which is bigger, this group or that group? Well, 3 atoms is bigger than 1. So this is big, this one's small. And it turns out this is the orientation that's preferred in the reaction. You got the bigger group not lining up with the other big group. So they're doing the opposite, right? Just to minimize crowding. The hydrogen to attach the boron in the small group, so put that closer to the bigger group of the alkene. And then 2 arrows will finish our mechanism. I think of the pi electrons as attaching to the boron, but it's going to connect this carbon to the boron. So I say, hey, these pi electrons go in between the boron and the carbon. And this bond between the boron and the hydrogen break and connect this hydrogen and this carbon. So what does that mean? These 2 electrons need to go in between the carbon and the hydrogen. So the alkene carbons are here, hydrogen got attached here, and the B, the boron, got attached there, and it kept its two hydrogens. And then later, after multiple steps of the first reaction and the second reaction, the boron gets changed. So pair of arrows saying, yeah, a couple steps, several steps later, where the boron used to be, that's where the alcohol ends up. And the hydrogen from BH3 is the one that went to the carbon with fewer hydrogens, anti-Markovnikov product. I'm putting in parentheses because you don't have to show this part on the exam. If I ask for the mechanism of hydroboration, just get your groups oriented the right way. The hydrogen of BH3 closer to the bigger alkene carbon, two curved arrows, and you're done. Nice. Let's end this video with a quick little summary of anti-addition and syn addition. Okay, let's clean the screen a little bit, sorry. There we go. Make sure I didn't forget anything. We talked about syn addition, we did. Very good, last example. Yeah. Okay. New structure. Let's get 1,2-dimethyl cyclohexene and do a couple things with it. Let's react with Br2. Okay, so what reaction happens there? Well, the pattern is, and we don't have to do the mechanism. I just want products. So the question might be predict products. Okay, so Br2, ooh, the double bond is in a ring. So now I have to worry about trans or anti-addition. So one bromine goes to one alkene carbon, the other bromine goes to the other, and they are opposite. So the pattern is double bond changes to a single bond. One bromine is wedge, the other bromine is dash, and you get a pair of enantiomers. I chose just randomly, top bromine is wedge. You get the other product. Which has the top bromine dash, the bottom bromine would be wedge, be opposite. And then what became the methyl groups? They're still there, they just got pushed out of the way, right? This is an alkene carbon, which is sp2, flat trigonal. So bromine, well, I have the top bromine coming from the top, pushing the top methyl away. And then the bottom bromine came in from the underneath the ring and pushed the methyl group towards us. And that's our product, plus the enantiomer. So switch your dash and wedge bonds. That's the enantiomer. And then I'll ask, hey, is this a cis or a trans product? You can use cis or trans in the name because we do have identical groups. You could say, well, the identical bromines are on opposite bonds. Or you could say the identical methyls are opposite bonds. This is trans. That's a trans product. And it came about through anti-addition. In the mechanism, one bromine added to the side opposite the first bromine. That's the definition of anti-addition. How the bromines add opposite to each other. And you got trans product. Cool. Let's take the same molecule and do hydroboration oxidation with it. You can put a dot, you can put a slash between BH3 and THF, all those different variations. Hydrogen peroxide, you can put OH minus or sodium hydroxide, potassium hydroxide, whatever you want. Okay, what happens here? Well, it happens by syn addition. And the hydrogen goes to the carbon with more hydrogen, fewer hydrogens. It's anti-Markovnikov. How many hydrogens are this alkene carbon? None. This one? None. So you're going to get a mixture. So I'm just going to draw one of them. Let's pick the alkyl group going to the top carbon. Okay. So pattern is pi bond, double bond, goes to a single. Syn addition means these reagents are going to make an alcohol. One alkene carbon gets an H, the other one gets an alcohol group. So I'm just going to randomly pick the alcohol to be on top. And then syn addition says the hydrogens have to be together. What became of the methyls? They got shoved out of the way. The wedge bond's already taken, so methyls, you have to sit on dash. Yeah. Cool. You also get the other product too, enantiomers and all that good stuff. All right. Is this a cis or the trans product? Well, where are the identical groups? The methyl and the methyl are the identical groups. So this, and they're on both on dash. This is the cis product. Very cool. Okay, it's at this point students see the pattern and say, ooh, anti-addition means trans product. Syn addition means cis product. Got it. That's all I need to know. Thank you, Dennis. Bye-bye. And I'm like, ooh, no. Let's take away a methyl group. And let's do hydroboration again. It's the same exact reaction. It's got the same mechanism. You're missing a methyl group, so just take away a methyl group in the product, right? Pretty much. Let's see how that works. It's still syn addition. More importantly, it's anti-Markovnikov addition. So these reagents say what goes on to the molecule. They're going to say, put an alcohol, an OH group on one carbon, put an H on the other alkene carbon. Where's the H go? Markovnikov's rule says hydrogen goes to carbon with more hydrogens. But this is anti-Markovnikov, the opposite. So hydrogen, you go to the carbon that has fewer hydrogens, right? So hydrogen's got to go up here. So here, I'm going to attach the hydrogen. Checking my notes, make sure I'm doing this right. Yes. And now just pick one. There's a dash of wedge. It could be either one. Make sure enantiomer. So I'll just pick wedge like I did here. And then the alcohol, ooh, you also have to be wedge. Nice. And now, okay, for the top methyl group, where's the methyl? Well, it's still attached to the top carbon, but it got shoved out of the way by the hydrogen. And now it's on a dash bond. Hey, I got a wedge bond here. What's on the dash bond? Well, what was here already? The missing hydrogen, right? Carbon makes 4 bonds. I only see 3 lines, so there has to be a hydrogen. Cool. We got syn addition again. The new groups came in together, side by side symmetrically. That's syn addition. It is syn addition. But now let me ask you, is this a cis or the trans product? If you use cis or trans in the name, which you can, you're talking about the identical groups. Who's identical here? The hydrogens are identical. Well, one's wedge, one's dash. This is the trans product. It is. It's trans. Okay. So syn addition, does that always mean cis product? Nope. Anti-addition, does that always mean trans product? Nope. Maybe for BR2, because BR2 is always identical groups. But there are other anti-addition reactions. Halohydrin formation, for example. So be a little careful. That's why there's 2 sets of terms. That's plenty for today. Thanks for watching.